Hello everyone, welcome back to this next lecture. So in this lecture I'm going to show you how we can execute this project, and in this particular example I'm going to show you a slightly different way of verifying our results, because now you need to see whether the ADC values have been read correctly, and for this I'm going to use a slightly different approach as we did in the previous lectures. So as always, I'm going to bring the microcontroller into the video. So you will now see the microcontroller in the video. Most of the connections are the same. The only difference is now we are connecting the other terminal of the capacitor, that is the positive terminal of the capacitor, to our analog input pins. And these are the additional connections which have been made. So I have made connections from these terminals to pin A0 and C3 and to pin A1 and C5, right? So these are the analog pins that I have chosen. If you've chosen something else, please make those connections accordingly. Now, with this, I'm going to zoom in on the oscilloscope because we are not doing any changes in the circuit in the solderless breadboard. So you will now see the zoom in of, or at least a zoomed in waveform, at least the oscilloscope zoomed in. So with this, I'm now going to go and start compiling, or rather downloading the code. And the usual choice. So as usual, I will select it and I will run the code. So if you look at the waveform now, you will see the usual sawtooth or triangular waveforms that we saw in the previous lecture. So therefore these are the analog signals, or rather these are the signals that we are feeding to the analog pins of ADC-A and ADC-C modules. So now the question is, how are we going to view the results of this? So for this, I am going to first execute CPU2 as well. So first I will do the usual, I will connect the target and I will go to run and load the program. So I go to the driver lib project, CPU2 RAM, and I click on .out file. So this program is running. So with this, I'm going to end the microcontroller video because we don't need that anymore. What we need now is the debug window, and I'm going to show you how we can use that. So now that we have only the debug window, and now we have both our code running, and we know for sure that we are producing those analog signals and that we are feeding the analog signals into our analog pins. So the question then is, how are we going to verify whether our code is running correctly? So the first thing we're going to do is, let's go to CPU1 because let's do our connections with CPU1. I'm going to just close this for now. And here I will ask you to go all the way up and check out these variables, global variables. So this is the bitfield project, and in the bitfield project I had defined these global variables. These global variables are being assigned to values here, and we had calculated these values for given the fact that the analog signals are between the 0 and 3.3 range, right? So now the question is, can you view these variables? And the answer is yes, you can. You can use this particular debug window to observe variables that you have defined here. The only condition is that the variables have to be global. You cannot observe variables such as volt draw and current draw which are local to functions. So for that, I will show you that we can come over. Let me just collapse this and I will expand on the watch window. So this watch window is what is normally used to watch any variable, right? So this watch window has all these, and to add a new variable, you click on this plus button. Now here you enter the name of the variable that you would like to watch. In this case, we are looking for the volt variable. So therefore we click on it, and you will see that this volt variable has a value. So let me just expand on this. It has a value because it is a double value. But the question is, the value is not changing. the value is not changing because this has been read only once. If you want it to be refreshed, you will see there are these buttons here. This button will refresh the value, but it will refresh it only once. You have the option to do a continuous refresh, and that next button is this. If I click on this, you will see now that the value is continuously changing. This is the value of the analog input that we are feeding into this. So now you can also add the other one, which is current. And both are now in continuous refresh mode, and you will clearly see how they are changing, right? You will see that they are changing, and both of these are changing continuously between 0 and 3.3 volts. Now, of course, you can do a lot of other things. For example, you can measure the maximum, you can measure the average, and you can then store them as global variables and verify for yourself what the value is. I will not do that here. That is unnecessarily going to extend this particular project, which has already gotten pretty long. So therefore, this is a way of actually verifying that your code is working correctly. What this means is we have configured our ADC A channel correctly. We are able to actually convert it correctly, and we are measuring these values, or rather we are converting them back into floating point values, and these are also looking okay. So now that we have reached this stage, let's go do this for CPU2. Now if I go over to CPU2, you will see that these variables show up again. Now you might think that in this case this is for CPU2, but this is actually a problem. We have defined the same variable for both bit field and driver lib, and that can sometimes be an issue because the variables that are in the watch window are sometimes common to both of them, right? So what I am going to do is, if to remove a variable, we can just press this cross sign next to it. You can see the helper comes up, the tip comes up, which is remove expression. So I'm going to remove both of these, and let me close this, stop this execution. Now what I'm going to do is, I'm going to go to my bit field and driver lib, and I'm going to change the name of these functions, or these variables rather, so that we explicitly know what variables we are changing and we are observing. So I'm going to call the variables in the bit field project volt1 and current1, and the driver lib project I'm going to call these volt2 and current2, right? So now we explicitly have different variables for the bit field for CPU1 and CPU2. So once this is done, let me come over here and I will compile this again and build it. And there are no errors, so I'll come over to driver lib, clean it and build it. So we now have two different sets of variables. So let's go now and try to put the watch on this. So as usual, I will go into debug mode. I will select CPU1 and continue. And let me run it. So now that this is running, I am going to now add those exact variables which I had defined. So I am going to add volt1 and current1, right? And we get back pretty much the same thing which we got back before. But now comes the interesting part. If I'm going to click on CPU2, you will see now it says clearly that these variables are not available. So this shows you that what we were seeing before, that is the volt and current value, were not necessarily correct. So what I'm going to do is, I'm going to add two other variables, that is volt2, and let me just pull this up a little, and I will add current2. So currently CPU2 is disconnected, and that is why it says it is not available, because we have added variables which are not even produced by this particular CPU2, right? So of course, as usual, you know the method to go about it. If you switch over here, you will see again we get our volt1 and current1, but we don't get volt2 and current2. So at least we know that our observations are still okay. So you can just go into the continuous refresh mode and you will see this is still changing. So now that we are here, now let's go over to our CPU2 and let's connect it. So it is connected. Let me now load the program. And now let's run this code. So now you will see something very strange. Nothing is happening in volt 2 and current 2, right? We have the continuous refresh mode open, but still nothing is happening. So that means there is a bug. There is a bug in this code somewhere. Now to be able to find out what is the bug, you go into the register view mode. So for example, if I go into view and I come all the way down here, you'll see there is an option called registers. This shows you what are the value of the registers that are there on the CPUs. So if I click on this, you will see now another window opens up. These are all the registers which are there. So now the question we can ask is, you'll see these are all listed out. So there are some core registers. We don't want the core registers. What we want are the ADC C result register. So let's go see if we are getting a result. And if you go into ADC C result registers, you will see that there is no value here, right? ADC result 0 and ADC result 1 are 0. Let's go into synchronous mode, or rather continuous refresh mode, and you will see that also has no impact. Now I'll collapse this for a while and let me come over to EPWM1 regs and just show you how this works, or rather EPWM4 regs, because this is CPU2. And you will see that since I am in the continuous refresh mode, you will see now the TB counter is working. This is the value of TBCTL, right? So these are all the configurations we have made and you can verify them here yourself. So this is a great way to know that your configurations have been made the way you expect them to be, right? So you will see all these configurations here. So our PWM is working. So now let's go over to our ADC module and figure out what is wrong there. So we should go to ADC C regs, sorry, not ADC D regs, but ADC C regs, and let's check out what's happening. So you see we have ADC CTL1 and ADC CTL1 has these particular ones, right? Now in this I realize I made another bug. We have forgotten to set this pulse bit to 1. This is also something we need to rectify in the next level. So now that this is done, let me collapse this. And let's go over to the int flags. So you see these are the interrupt flags and you see nothing is actually set, right? So nothing is actually set and we know that there is no flag being generated. So now let's go over to our actual control registers and figure out what is going on. Now there is one major problem you see. You see there is no setting for ADC SOC1 CTL. This is 0. There is only a setting for ADC SOC CTL. And let's take a look at what this is. And you'll see this is not what we want. Trigger selection is okay. But you'll see the trigger select, the other one, channel select. This is not the channel select that we had chosen. If you come over here and have a look to driver lib, and let's come all the way down here, you will see that this is not what we had set. We had set a value of 1.8 and 2.8. And this means this is number 3 and this is number 5. So we should be seeing the number 3 here and we should be seeing the number 5 here. So that means this value has not been written correctly. So this means this is our problem at this configuration. And you can very clearly see what the error is. If you had picked it up when I was writing the code, then that's fantastic. If you don't, then here is the error. We are writing the same register again. That is, we are writing ADC SOC CTL and here we are writing ADC SOC 0 CTL 2 times. This should be ADC SOC 1 CTL. So this is a mistake. So this is something that we must correct. So here I'm going to stop this and let us go and make this change. So the first thing is, this is a simple mistake and I will just correct it. And let me collapse this for a minute. And the next change we need to make is with respect to the ADC int. That is, we need to make sure that we have configured the interrupt pulse to be 1, so that the interrupts are generated when the EOC is generated and not when the SOC is generated, right? So let's come over to our technical reference manual and let's go over to the table. So here you will see there is the int pulse bit. So this int pulse bit has to be set to 1, which means we have to write the number 1 to this bit, which is the number byte 4. So let's go and write the number 4 to this bit. So I'll just come up here, this should be here. I'll copy this. And this is within EAllow, so we should be okay. And I'm going to paste it and I'm going to write the number 4, right? So this setting is simply to ensure that the interrupts are generated when the end of conversion is issued and not when the conversion begins. When the conversion begins, which you can see here, when int pulse is equal to 0, the default is that occurs at the end of the acquisition window. This is too early. We want the interrupt pulse generation to occur at the end of the conversion, right? This is when we know the results are available. So with these changes, let's come up here and let's compile our code. So this is working. This is the Bitfield project. Let's come down here and compile the driver lib project. And this is also working. So now let's go into debug mode with the Bitfield project, that is CPU1 project. So we are back here again. So I'm going to run this and you can see since we are in continuous refresh mode, we get back these same changing values, right? So again, if you want to expand on this, you can just check it out. These are the values. So now let's see if CPU2 works. So again, we go into this and we connect target and I will load the program. And we choose the .out file, click OK. And now we end up with the values. So you see, this is how we were able to debug our issue. And if you come now here and let's look for the ADC result registers, let's look for the ADC result registers. You'll see now the ADC result registers are changing, which means now these values are being continuously changing as it is receiving signals on those pins, because now the converted value is being written into these result registers. And at the same time, if you come over here to the ADC-C registers, you will see now every now and then that the int flag is also being set, because this means that an interrupt is being set. And of course, the interrupt is being cleared almost immediately in our control code, and therefore you do not see it all the time, right? But the important thing is now you're seeing these values. So let's come over here and have a look at now our ADC SOC CTL, and now you will see the correct value has been set. Both values are now correctly set. That is, ADC SOC CTL has a channel selection of 3 because we are selecting ADC in C3, and for ADC SOC1 CTL you're seeing the channel selection is 0x5 because it is the C5 pin that we are connecting to our ADC SOC, ADC SOC1. So this is a way of actually viewing variables and also debugging your entire code, because every now and then you will find that your programs don't work, and it could be for various reasons. Like we saw just now, we saw that this time we had made a typo, at least I had made a typo rather. Therefore you could see from that typo that the registers were not written in the manner we expected it to, right? I was expecting to see channel selection here to be equal to 5, and I was or rather 3, and here to be equal to 5, but we saw 7 and this entire register was 0. So this clearly shows that we were not writing our registers correctly, and therefore you now know where you need to go and figure out where the bug is in your code. So this is a very, very powerful technique of actually debugging your code of viewing results. So for example, you can always view results, and this way you can actually have several types of logic to check what is happening in your code, right? You can have flags, you can set those flags to values. So if those values attain certain values, you know that the code is working correctly or not working correctly. So all these things are now possible because of this debug window. So this is a very, very powerful option, that is the watch window as well as this register window. And in case you're wondering how it comes, you just have to go to view, come all the way down here and look for registers, and this window will open. And once you're done with it, you can close this window and that's it, right? So this is how we can debug our code, and with this we now know that our code is working. So if you switch over to CPU 1, you will see volt 1 and current 1 will change, but volt 2 and current 2 are not available because these variables are not defined in CPU 1, they are defined in CPU 2. So with this, I will bring this lecture to an end. We have now configured our ADC modules correctly. We have chosen our channels, and we are able to measure, or rather we are able to observe the changing signal values on our variables in the watch window. So with this, I will conclude this lecture, and in the next lecture I am going to conclude on this section. If any of this did not work for you, or you have faced any other issues, and there is, just in case to let you know, every time you're using this, there could be issues such as you might lose connectivity, and once in a while you might have to then reconnect your system and rerun your program, because this debug mode is sometimes prone to disconnection and hanging. So this is something you must keep in mind. It is not completely glitch free. There are glitches and there are possibilities where you could the entire thing could freeze. So other than this, if you faced any other issues, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening and see you soon. Goodbye for now.